He is a senior engineer at Applied Blockchain, and he's going to be talking to us about the London Bridge. And this is using Algorand state-proof technology. So some very exciting things that Matthew is going to come up to the stage and tell us all about.
Welcome, Matthew.
Is this on? Oh, yeah, good. So this is one of the first times I've actually used a handheld mic. So any times I sort of blow out your eardrums because it's either too close or it's too far away and you can't hear me, please just shout at me and go, hey, the mic's too far away from you. But hello, thank you all also for inviting me. This is my first ever time in Asia, so it's quite an exciting experience, even though I'm struggling somewhat with the humidity. And I'm here as one of the senior developers at Applied Blockchain who are working on the London Bridge product. And I'm here to explain to you what the London Bridge is, and specifically how we've incorporated state proofs into the overall design. So sort of the outline of the talk is that I'll be sort of introducing what bridges are, why we would want to use them in the first place, give sort of an architectural overview of the London Bridge product, and then take a deep dive to explore where, why, and how we incorporate state proofs into the London Bridge. Now, hopefully, when I click next, it goes next. Brilliant. So first of all, who are we? So I work for Applied Blockchain, and we're a company of about a team of about 100 developers, sort of split between the United Kingdom and Portugal, with our main offices in London and Porto. And since 2015, we've been developing blockchain applications for a wide range of different companies and sizes, from very small startups to very large companies like Shell, for example. And really, we're just a team of techies. We love blockchain because of the technology behind it. We nerd out about it. And that's why, really, since the inception of Algorand, we've been developing applications on Algorand. Why? Because as techies, we really are interested in the technology underpinning Algorand. We're big proponents of it. We enjoy nerding out and talking about things like state proofs, ZK snarks, proof of stake, and things like that. And also, it's quite an exciting blockchain to be a partner with, because as we've seen today with state proofs, Algorand are continually at the edge of technological innovation in the blockchain space. So really, it comes as no surprise to say that really Algorand is part of the DNA of Applied Blockchain. And so therefore, we're really proud to say that we are an Algorand partner. Indeed, the London Bridge was supported by an Algorand Foundation grant, including some of our other products. And I hope during today's talk, I can really sort of let you in on what it really means to be an Algorand partner, because certainly we've been actively communicating with people like Noah and the rest of the team about what state proofs are. Obviously, we had to learn it for ourselves. It really is the best way to incorporate them into our bridge in the most secure way possible. So why do we need bridges? So as the popularity of blockchains has increased, there have become more and more layer 1 blockchains, which generally reside in their own little island, with no native way, really, to establish secure communication channels between those blockchains. And by communication channels, I really mean ways to transfer assets, token data, etc. So, but on one hand, interoperability seems to be one of the key words of this today's sessions, and that is really driven by the fact that we're more turning into a multi-chain world. Hello? It seems to keep. Does it keep on cutting in and out? Okay, right. I'm just trying to speak a bit louder. But we're really going to a multi-chain world where people who develop on. It's a bit freaking out. Where we develop applications on not just one blockchain, but we really want to leverage the users and liquidity on several blockchain ecosystems. But in order to do that, we need to have strong interoperability protocols in order to do that securely. So one of those particular type of interoperability solutions would be something like a bridge. So to discuss sort of what a bridge is, we're going to take the Trustless model, and it's called Trustless because the bridge is really all the logic in the bridge is underdone in the blockchains themselves, so there's no more trust required outside of the trust you have in the blockchains. So let's imagine we've got someone who wants to transfer £10 of their X tokens on blockchain X, and in the end of it, have £10 of Y tokens on blockchain Y. So the general process is that they would deposit £10 of X tokens in a smart contract on blockchain X, which would then lock those tokens. And that's really important. And the reason to try and understand that, just try and think of what happens if you didn't lock those tokens. If you didn't lock those tokens and blockchain Y then just minted £10 worth of Y tokens, the person using the bridge would still have £10 of tokens on blockchain X and £10 of tokens on blockchain Y. So instead of transferring tokens, they've just duplicated tokens. And printing money isn't really what we're about in this industry. So we have to lock the tokens on blockchain X first. And therefore, blockchain Y, before they mint, has to be reasonably confident that on blockchain X, those original tokens have indeed been locked. And so in sort of the general overview of this kind of process is that blockchain X would generate a proof that those tokens have been locked. That would be sent then to blockchain Y, who then, using that proof, basically asks yes or no questions to that proof, basically going, hey, have these tokens been locked on blockchain X? And if you get a yes answer back, blockchain Y then mints those tokens. So I've titled this as Deceptively Simple because there's been two assumptions I've made here. One is that blockchain X has the technological capability of generating such proof. And the second is that the cost of the verification directly on blockchain Y is powerful enough for consumers to use the bridge itself. So here I'm really thinking about case studies where you'd be bridging to something like Ethereum with gas fees, and that could be a prohibitively costly step. So what's happened is that bridges have sort of created some middlemen in between blockchain X and blockchain Y. And without going into too much details, they could either be a single operator or they could be a committee. And essentially, they form a consensus about the current state of blockchain X. Then blockchain Y would ask those middlemen, basically, has that token been locked? And those middlemen really sort of replace blockchain X with respect to in the eyes of blockchain Y, because now the source of truth about the state of blockchain X is coming from those middlemen. Now, that obviously increases the level of trust you need to have in the bridge. And although some of them could be implemented securely, a lot of them aren't. So we have this position in this sort of ecosystem where we have lots of blockchains underpinned by very strong cryptographic technologies, but then are linked together by these quite rickety bridges, as someone mentioned earlier. And this is a concern because currently there's about 320 million, $30 billion, let's get the correct magnitudes, $30 billion locked up in these bridges. So it's a bit concerning that some of them are, from a security perspective, a bit dodgy. And indeed, hackers have also noticed that. So what's happened this year is really the annus horribilis of the blockchain token bridge industry, is that we've had a number of high-profile hacks. And these hacks have made their way to mainstream media. They've grabbed attention simply for the headline data point that nearly $2 billion have been hacked from bridges year to date. And this was, inevitable. And so Adi, our CEO at Applied Blockchain, was talking about this at Decipher in November, is that if you have insecure bridging technology, you are far more likely to be hacked. And considering the amount of liquidity in these tokens, it's really prime game for hackers in terms of trying to get some money out of the blockchain world. So really, we want to go back to the original Trustless model, where the bridge is really residing in the blockchains themselves, not relying on these trusted intermediates. And so here we have to solve those two problems I was talking about before. Does blockchain X have the required technology to generate a proof? And also, is that proof, in terms of verification and cost, able to be done on blockchain Y cheaply enough? So Algorand's state proofs solve the first problem for all proof-of-stake blockchains. So really, the state proofs really are just sort of like an interoperability protocol for those proof-of-stake blockchains, which allows them to establish secure communication channels between other blockchains without recourse to these trusted intermediates. But those state proofs are still a little bit too expensive to be verified directly on a chain like Ethereum. So Algorand are working on that solution with ZK Snarks. But in the meantime, we're happy to announce, talk about today, rather, London Bridge version 1.0, which, as well as leveraging the state proofs technology by Algorand, we've sort of included also Intel SGX enclave technology. And this basically is just secure, cryptographically secure pieces of memory in your CPU, which cannot be accessed from the outside, so it provides verifiable, trustable, and tamper-proof execution of code. And we have that residing inside the enclaves, and so we can take that verification code from running on Ethereum, for example, and place that in an enclave. And therefore, that reduces the actual real-life cost in transferring your assets across a bridge. Now, there is obviously an increase in trust from the trustless model. We're obviously not just using blockchains anymore, but that trust is tied into the technology underpinning Intel SGX technology, which has been an established trusted execution environment solution for many years in the hardware security industry. So it's not quite as bad as some of the other bridges, which is basically the trust is based on a couple of guys coming up with a protocol. So just sort of like the 4 pillars of the version 1.0, we rely on secure enclave technology. And so key point here is that you can hide secrets inside your SGX, and one of those secrets is a private key. And using that private key, the SGX, once it's finished, verify that there was a lock transaction on blockchain X, for example, it can sign a message and send that off to the smart contracts. So in essence, the enclaves are the ones controlling the smart contract operations. There's no need to trust the operators because the operators themselves have no idea what that private key is. And then there's a technical bit, which is attestation. We won't talk too much about this, but it's just a way for our tech-savvy users to verify that the code we're saying that should be running is running inside an enclave, and it's running in an actual enclave itself on a secure chip, rather than some simulation which some hackers can utilize. And then also in designing our UI is that we really want to make this as easy to use. And token bridges, in some respects, are quite easy to subscribe. We're just transferring tokens from one bridge to the other. So in reality, our users shouldn't need to know about SGX enclaves. They shouldn't really need to know about ZK Starks. They shouldn't need to know about state proofs, etc. So therefore, our user interface, as we'll see, is designed to make this complex process feel a bit more simple and intuitive, and therefore reduce the learning curve required to understand what's going on. And then lastly, if you ever used a bridge, and once you've locked up those tokens, it sometimes takes a long time for those tokens to appear on the other side. And so what we have is a clear and informative UI which helps us describe that process. So here's the UI. Like I said, it's quite simple. You can just enter your transfer details, then you confirm the transfer, and then while the transfer in progress, it sort of gives you a real-time update of where your tokens are in the bridge. So in terms of a high-level overview, there's 4 main components. The smart contracts, which deal with sort of the token locking, minting, redeeming, burning, etc. Then we have the processing enclaves, whose responsibility is to verify transactions such as a lock has taken place, either on Ethereum or Algorand. And they sign messages attesting to that fact, which then get sent into the smart contracts. Then there's the relayers, which simply just shuttle messages between the enclave and the smart contracts, and also pass relevant information about like state proofs and block headers, and transaction proofs as well as the enclave. And then the UI as well, which allows you to connect multiple wallets to the bridge. So I think just for time, I'm just going to briefly go over what this is. So Intel SGX creates isolated secure areas in a CPU where secrets can safely be stored, like private keys. But just for time's sake, let's go on to an example use case so we can talk about why we use state proofs in the bridge. So what happens is that, let's just say our guy is now using our London Bridge. So they deposit transactions in the escrow smart contract. They get locked. And then our relayers monitor sort of the Algorand blockchain for that kind of type of transaction. And when it finds that, it then retrieves the transaction proofs from Algorand using something like Algod. And then it feeds those into the Algorand processing enclave, which does two things. One, it verifies that transaction is a transaction to our smart contract. And the second thing it does, it interacts with an Algorand-like client. And that Algorand-like client really answers yes or no questions about a specific domain of knowledge about the Algorand state. So the domain of knowledge here is that, well, has a specific transaction occurred in a specific block on the Algorand chain. And that is where state proofs come into it. But just carrying on, so once that's been attested to, and everything's been verified and everything's OK, the Algorand processing enclave signs the message using the secret private key, which only it knows, operators don't. It then sends that via the relayers to the Ethereum token contract, who then verifies that message, signature using the stored public key. And if everything's OK, we then mint tokens because Ethereum is now confident that there has been a locking of tokens on the Algorand chain. So I don't know how much time I've got left, but really, so why do we use state proofs? So state proofs allow one to create a light client for the Algorand blockchain. And the way it happens is that the light client ingests these state proofs, it verifies it, and after that verification, if it's successful, you basically get a block interval commitment. So this diagram is taken by a fantastic guide by, I think, Noah, and really sort of attests to the fact that, although this is very technical, the Algorand team are very well aware of that and try their best to sort of communicate these ideas to even simple-minded folks like myself to try and make sure we can understand it properly. So I think this is fantastic, hence why I just nicked the slide. So sorry, Noah. So we've been working, so what I was saying is that once you verify that, you get these block interval commitments. And what they are is really just a set of transaction routes for every block that was contained inside the block interval. And then a second step is when we get fed in transaction proofs into this light client. And what we do with those transaction proofs is we calculate the supposed transaction route. And then we use that the block interval commitment, to verify this transaction route. So, I'm not going to go into too much more details than that, but what I really want to point out is that we've been working with Algorand quite considerably with this. We've been in constant communication with them since probably the beginning of February about what is the best ways we can incorporate these proofs, and also explaining what they are. And then what Algorand did was create their own verification code. So this is verification for the state proofs. So we've incorporated that into our enclaves. So it isn't our verification code you're relying on. You're relying on the verification code developed by Algorand, their team of cryptographic experts. And also what they did to help facilitate the use of light clients, I think in this document here, is they outlined a proof of concept for the light client itself. So this has been a very useful guide for us when developing the light client inside the enclave. And really, if you guys want to use state proofs, definitely look at this and the links inside for a really good and in-depth understanding of the best way to use these state proofs in your application. So like I said, I just want to say thank you to Noah, Gary, and the rest of the team for always being open in their communications with us, probably a bit patient with some maybe our dumb questions and going, are state proofs ready yet? Which they always went, no, not now. But we're glad they have arrived, and actually, with their help, it's really fast-forwarded the process of incorporating these proofs into our London Bridge. And then I was also asked, well, as a developer, what is it like to be working and building on Algorand? And I just want to say I'm quite new to the blockchain development world. I've only really been doing this since January, so I really have to pinch myself to think, how the hell am I here? But really what I just want to say is that Algorand are really conscientious in making the onboarding process quite smooth for new developers like I was, and quite honestly still am. And so, first of all, main protocol that I found that was really helpful was the Algorand developer portal and also the YouTube channel. So the YouTube channel has got a great series about what is Algorand, how to form your first transaction, what exactly is proof of stake, etc., and things like that. And the Algorand developer portal, although it contains all the information you ever want and more, it's really designed in a way so new users can look at it and get the introductory material straight away, which isn't always the case with encyclopedic material, where you sort of have to sift through the technical stuff to get to the introductory material for us. And also Discord, I found that they've been exceptional in responding to us and helping us in terms of developing this work. So there was a guy, Barngy92, I think he's called Benjamin, I've forgotten his name. Someone's nodding, so I must have got the right username there. So when I asked a technical question about how does one generate STIB hashes, instead of just giving a list of bullet points, he actually gave and took up a lot of his time, to be fair, to write workable code. And so, yeah, big shout out to him. That was really helpful. But Discord is often very fast response by experts. So that's great. And then in terms of corporations, we have a Slack channel with Algorand, which we continually pester the Algorand team about all sorts of various technical information. And they very graciously always take the time to talk to us and respond. And then also, and people like Noah is on our Slack channel saying, oh, this protocol update is really important for you guys. You have to change your API, or this is the state proof. This is the state proof introduction. So really what I want to say is that building and working with Algorand is really a partnership. We are an Algorand partner. They're very open in communication with us, and they help us a lot in developing these applications. And I think that's all I have for today. So thank you very much for listening to me. And yeah, have a good rest of the day.
Thank you very much, Matthew Bailey. Yes. Matthew, we have just a couple of minutes maybe to field a couple of questions, or at least one.
Sure,
so if you've got one, we're going to put your hand in the air. What kind words Matthew has to say about my team, the Algorand developer relations team, and our documentation? Thanks very much. Here's our question.
Hello, Matt. You're saying that you did the safe enclave as part of the process for doing that? The safe enclave, the hardware.
Oh, yeah, sorry, yes, enclave, yes. So I didn't talk about that in too much depth, yes. So in our version 1.0, because currently state proofs are just really too expensive to be verified directly on Ethereum, for example, we use this very secure technology in order to verify the state proofs inside that.
So that means you cannot use Windows then? Because that is Intel, right? You cannot use...
Oh, no. So it's almost the inverse of that. So Intel SGX is really Linux-based.
Okay.
Yeah.
And
so yeah, so it'll be residing on our servers. So a user will never download this. But it's on servers and distributed and things like that. So that doesn't matter from a user perspective.
Matthew, I think we have another question right here for you.
Yeah, sure.
Thanks so much for the presentation. I'm really interested in the proof space as well, and specifically for Intel SGX. I wonder, how do you see the compensation for decentralization and also kind of future longevity, as there are more like edge cases, clumsy instructions? So like moving forward, how do you plan to build these TEE into the system?
Okay, yeah, so I mean, in terms of the long-term plan, we want to move to a fully trustless bridge. So that would be the end of SGX in our London Bridge architecture. So there's various things we can do. In the simplified version, I was just relying on one enclave, but you could sort of have like a distributed systems of enclaves, and then you can sort of poll that to make sure they agree on a consensus, whether they're verified or not. But in the long term, we are looking to remove, like I said, move towards a trustless architecture. So this is like a short stop solution. We can discuss it a bit further. But in terms of Intel SGX and London Bridge, once ZK snarks are out, we'll look to move to a fully trustless bridge.
Look, I think you've left enough time for one additional question. Do we have it out there? All right. Matthew Bailey. Thank you very much for telling us all about the London Bridge.
Right, thank you.